Hello, guys. Uh, are you able to hear me?
Yeah, we can hear you.
Yeah. I was supposed to start the presentation first, and the lesson 12, I just had one day, so I thought I'll just do the mini presentation
Mhm.
of sort. I did a deep learning project at CERN last semester, and it was quite interesting. So I thought I'll present on that. And lesson 12, I tried to do it, but it's really huge, and even the edited video is not up, not the notes, anything. I tried till the first hour, but the rest of it is I still have to read the paper and the notebooks. So anyone else have completed lesson 12, or at least have a like much better grasp than me, willing to take over? No? Okay.
Yeah, there hasn't been time to go through those notebooks and really study them carefully. There's so much material in there, and yeah, it's going to take a little while.
Yeah, I'm still stuck on the paper, the ResNet that Jeremy said, and the notebook, and that's a huge, lots of concepts there. So
Yeah, and even the whole NLP was within an hour. That's what I observed. I said he started NLP and he's go boom, 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 all ULM stuff, and then that's all of a sudden it finished within an hour. So plenty to take on, I think, in the last hour as well.
They're really living up to the promise that it's going to keep us busy until at least the next course, at least.
Yeah, that's correct. Yeah.
mhm.
So, Staniam, could you tell us about your Kaggle competition?
Sure. About the pet finder competition.
Yeah,
the one that you did well in.
Sure. I'd also point out the links in the chat as well.
Mhm.
So it was a kernels only competition. So I did join the team, but I did not have a lot of contribution, so to speak, because I was more of an experimenter with the resources. I was not as well versed with the kernel-based competitions, to be very honest. My teammate.
What's this kernel only experiment and or the competition?
The recent one, Jigsaw, is a different story, but in general, kernel-only competition means that you're not allowed to train outside of Kaggle kernel. So you have some limitations that you're only allowed to use the GPU on the kernel for a certain fixed number of hours. So that severely limits down your solution to what a kernel is capable of.
Oh, I see.
Okay, so in a sense, like I think it's a level field for
It's a level field for sure.
competitors. Yeah,
It's totally about how beautiful solutions can you come up with.
okay, with the less resources, do more with the less.
That's right.
Okay, makes
The
sense.
Jigsaw one, it's a different story. So you can train offline, but inference should run on the kernel. So you can upload a model. I'm assuming I haven't checked, and you need to do the inference via the kernel.
So when about this inference, can you expand it a word this a bit? I have heard this in a quite couple of weeks more on inference. I think Jeremy used quite a lot as well. Could you explain what does we mean by inference when we are doing this machine learning, or when actually we are running it? Is it a testing or is it a validation or what?
It's the part when you're trying to predict the labels after you're done training and you stop your training. Then and there, that is your model does not get to improve. Furthermore, your epochs are done, and you're just uh, putting in data and pulling out labels. Just doing that. No more training.
Yeah, so inference is just running your model on a new set of data.
Right.
So is it a test phase when you're running?
It's after you're done. It's after you're done. Your model, you've done everything you can to make it as good as you can with validation. Now it's hands off. You can't touch your model anymore. You take that model, you take some new data, test data, and you apply the model. That's called inference.
I mean, it's sort of a test phase that you're but you've actually put it out in the wild. So your model is now set to do whatever it's supposed to do.
So in a sense, in terms of a Kaggle computation, is it the inference is like when you daily do the summation, your model, or is this is the final when the private board comes?
No, it's referring to the same scenario of the competitions. So just like you need to train the models for the competitions as well. It just refers to the part where you need to predict the labels.
Yeah, that's right. So what Sanyam said is right. All inference is taking a trained model and applying it to some data and predicting the labels. That's what inference means. It means after you've trained the model, you now apply the model to some new data and predict the labels. Does that make sense?
Yeah, it does. But in terms of the Kaggle computation we are doing, the question is it like you do the daily submission to see your score? Is that your inference, or is it the last phase when they run your model against the held out data, and then finally
it's synonymous with the general reference to inference.
Okay, so in the sense in general, so that's what I understood. The test data, when you run it against the unseen or the test data, and then whatever your accuracy comes in, that's the inference we are saying.
Right. So that phase is called inference.
Okay.
Some of the labels that you put out are in the public leaderboard as determined by the host. So that accounts for a public score. And some later on at the end of competition reveal your actual score.
Okay, makes sense. So sorry, go ahead. You were explaining your competition.
It was like, I'll just point out to the discussion that we put up. But if you have any specific questions, I'm happy to answer those. Apart from that, it's a fun competition. I'd still recommend, like, even though it's over, you might want to go out for a spin with it.
So refresh our memory. What was the goal of the competition?
Sorry, I lost you for a second.
Oh, okay. What was the goal of the competition? What was the challenge?
Sure. Let me just quickly share my screen.
Have we lost Sanyam?
I think so.
Yeah, he's about to rejoin.
बिल्कुल जैसे जाओगे नहीं हो सकते तो हर किसी के गलत करना ऐसा मानना चलो यार कभी भी जाना तूने अब कैसे को मुझे मेरा बदले चलो दिन में तेरी बिजली कंपनी की बत्ती को कराएंगे मगर अबे वो आकर वीडियो बनाना दिखाई दे रहा है सामने अच्छे से वीडियो बना फेसबुक पे डाल यूट्यूब पे डाल शेयर कर से वकील से रहने का जेल के बाहर
Hey, who is Avinash?
Maybe you can mute everyone, then
Yeah.
everyone talks, then
Hey, Avinash, can you mute yourself, please? So what's the story? Are we waiting for Sanyam?
Yeah, I think he's still on.
Yeah, he posted
Yeah,
on the group chat that he's gonna join. But
Oh, he's on now, it looks like. But he's still muted. Now he's off. I think he's having trouble connecting.
should we wait for him, or should we go on with the mini presentation?
Yeah, why don't we go on with the mini presentation?
Okay. I'll start sharing my screen. Someone please monitor the group chat.
Yeah, you got it.
Yeah. Okay. So can everybody see my screen now?
Yeah.
Yeah.
Okay. So in the last summer of 2018, I did my research internship at CERN. My project was titled Deep Representation Learning for Trigger Monitoring. Basically, I designed.
That's pretty cool.
Yeah. Basically, the idea is very simple. I designed a deep learning model to learn the representations of the trigger system for the particle accelerators at CERN. Now, those are huge loaded words. So let's get into some context so that you can understand the problem itself. So CERN is like the world's largest particle physics lab. Many of you, I guess, already know about that. It's located in Geneva, between the borders of France and Switzerland. It's a huge collaborative effort across 22 countries, I think. So the main research infrastructure consists of the world's largest particle accelerators that are ever built.
So Aman, are you a particle physicist?
No. I'm just a student. I'm just a student now. I was selected for the internship at CERN.
Oh, are you a physics student?
No, I'm a computer science student. I
okay.
specialize in deep learning mostly. Okay. So we have these 4 experiments, huge experiments actually, and a huge tunnel, 27 kilometers long, and the particles are accelerated close to the speed of light. I was part of the CMS experiment, one of these detectors. You can see on the other end. These machines are basically really huge. And inside each of these tunnels, you collide the particles and then record the collision data. So these detectors are like three-dimensional cameras that detect the collision events. Now the problem is we have 600 million collisions every second. That's a huge, huge amount of data. And the interesting part is most of them are quite normal, quite routine, regular physics events. Only a very few of them are actually interesting. About 1 in a million are interesting physics events, which can actually lead to a scientific breakthrough, just like how they discovered Higgs boson. So the question is, how do we manage these huge amounts of data from 600 million per second? How do you find that one event that's of interest? So we have, yeah.
Excuse me. So
sure.
a collision is that an event that then gives rise to all these three-dimensional lines, trails?
Exactly. Yeah.
So each collision is a really complex event in itself.
In itself, yes, yes. And it leads to a huge amount of data for every collision. Okay.
And those 6 million
600
data points you said, are those the images, or in what form of this data is collected?
These are actually three-dimensional images, you can tell them. These detectors, you can imagine them as like 3D cameras, and they are just capturing a snapshot at every 23 milliseconds. It's called a lumisection. There's lots of technical details involved, but the basic idea is there are huge amounts of data is being released every other second. That's the main idea here. So what we have is they have 2 levels of filters to filter it down into something that is manageable by the physicist. At the first level, we have 100 gigabytes per second, and you have to select events out of these. This is the first pass. Right now, what you're seeing is the second pass, and this is quite sophisticated algorithms selected by physicists. And together, these 2 levels of filters reduce the data. So this is the crux of the problem. You have huge amounts of data, and you want to find out something interesting out of that. So, okay. Yeah. So let's look at the basic idea. So what happened was we had lots of lectures, lots of telecasts, and of the lectures, interesting lectures, but not all of them are interesting. So I figured a way out how to find if the lecture is interesting or not. And this is just the fun part. So you can observe the behavior of the group chat. If it's really active and people were talking a lot, what it meant was that the lecture is quite dense and people are not really understanding because the physics is really heavy. But if the group chat is silent, then you can actually say that the lecture is interesting. Now, this is not a part of the project, but the idea, I want to explain it to the other layman crowd as well, because lots of other people were there that didn't understand deep learning, representation learning, and that sort. So the main idea is, what we are trying to do is to observe the group chat behavior to probabilistically predict the quality of the lecture. And can we do the same for the trigger monitoring? Can we somehow map the level 1 triggers and use them as a prior to actually understand the high level triggers? Now let's see how that works. So this is the basic design, basic overview. We have the CMS experiment. This particular experiment produces 1 collision every 25 nanoseconds. And like we saw in the video, not all of them are interesting. We need to find the interesting event out of all of those uninteresting events. So we reduce this whole trigger system is made to filter and reduce the event rate. And it follows a cascaded hierarchical design. The level 1 trigger, the L1 trigger that you see, is just a quick and basic initial filter. And then we have the high level triggers. These are actually designed by the physicists. These are very sophisticated in software. And together, this both L1 and the HLT, the high level trigger, capture the physics domain knowledge that is required to identify the interesting events. Now, this system is already there, it's pre-built. And the use case of this is we need to find out, check the quality of the data. How good is the data? It should not be like all of the data is very regular, very routine. We need to find out the interesting one and then give it to the physics and then physicists, and then give it, store it somewhere safe. So what we do is you trigger the you find out the trigger rates and then plot them against the pileup. The pileup is just a proxy for time. And then you check the rates for if it is diverging from the expected behavior. You see the red band, this faded one. That's actually, if the dots move out of that, it means that there is something, there's some problem. Now, the current monitoring system that is in place, it actually relies on a field expert. It's actually a physicist who keeps looking at these events. There are lots of algorithms, the level ones, and there are lots of connected HLTs, and they are quite correlated. So they look at each of these and then find out if, okay, there's some problem. It's not capturing the right amount of data, or there's some problem in the detector, or lots of other stuff. The things that it cannot do is it cannot exploit the correlation between the different L1 and the different HLT triggers. But the idea here is to use deep representation learning, learn the representations to, let's see if we can do much better than this. So let's go back, and we all know that deep learning is really good because it learns really good representations of the data. It does automatic feature engineering, and is much better at doing that. And autoencoders, as you see on the left, are the very quintessential representation learning networks, and it basically tries to reconstruct the input and learns the latent representations in the bottleneck. Variational autoencoders are slightly more interesting because they have an added probability constraint in the bottleneck layer, and it has an additional loss, Kullback Leibler divergence, scale divergence loss, and it can also be used as a generative model. So basically, I took the idea of the variational autoencoder, and then you have some amount of, you see, there is a KL divergence loss in the bottleneck, and then you have an added, due to this, there is an additional probability constraint of how the priors should look and how it should be sampled. So can we use this idea to somehow model this hierarchical design? So then we came up with this hierarchical latent autoencoder. As you can see, it's basically the same thing. What's happening is you have the latent L1 triggers, and then these give rise to the high level triggers. So we can do the same thing in the network itself. You put in the high level trigger data, and then try to reconstruct the L1 triggers from the bottleneck. And then again, using these L1 triggers, you try to reconstruct back the HLTs. Now the idea is very similar to variational autoencoders in that sense that in the variational autoencoder, what happens is you make the assumption that the distribution, the inner representations are coming from are Gaussian, and that's what the KL divergence loss tries to minimize. However, in this particular case, the modification is that we have an additional loss in this layer, which is not KL divergence loss, which is just a simple MSE loss. So you're trying to reconstruct the L1 triggers back here. So in this way, yeah.
Aman,
Yeah.
what if, I'm sorry, what if the distribution is not Gaussian?
Yeah, the distribution is actually not Gaussian for this case, for the L1 triggers. It's multimodal, actually. It has two peaks, and it depends. It varies from each different kind. There are lots of trigger algorithms, and each one has its own slightly different distributions than the
Right,
standard.
but if you're computing the KL divergence against a Gaussian distribution, then I don't understand how it works if the natural distribution isn't Gaussian.
Yeah, we are actually not doing KL divergence in the bottleneck. That's what done in VAE. Here, what we do is we do a simple mean squared error loss in the bottleneck instead of a KL divergence loss, and then expect that the mean and the standard deviation being learned here will be of the probability, will be of the distribution that is natural to L1 triggers. So we assume that L1 triggers are not Gaussian. We don't know what they are.
Mm-hmm.
And later on, we can, I've also done some more research on that using kernel density estimation and then trying to find out what the actual distribution looks like. And then we find out that the model actually learns that kind of distribution using just a simple MSE loss in the bottleneck layer. So did that answer your question? Okay. So this is how it looks like, and we'll see that if it works. And then we find out that it indeed works with a simple variational autoencoder. The loss is 9.35 to 10 to the power minus 6, and then we see improvement here. it might look very less, but given the amount of data that we have, this is actually a significant improvement over simple VAE. And how do we use this for anomaly detection, you ask? Is this. This is something that was, I didn't have the time because I was there only for 3 months, and my supervisors are continuing to work, and I work with them with this remotely. So when this slides were made, we were at this stage. But what happens is basically you throw in an HLT, and then you observe the mean and the standard deviation of the L1 triggers. And then you actually observe the L1 triggers and see how far they deviate from the mean. And based on that, you try to see if there is an anomaly, if this is not working correctly, or if it is not selecting all the interesting events and selecting all the boring ones. So this is the crux of the research.
So Amar, what did the actual distribution end up looking like?
The actual distribution ends up looking like a multimodal Gaussian, which has different kinds of mini peaks, and depends on, it varies from different L1 triggers. Actually, there is not a single distribution. There are lots of L1 triggers. There are like 1,013 of them. So each one is correlated to the high level ones at a different rate. So each one looks slightly different. But then the distribution was captured by this mean and the standard deviation. Now you can also say that we also thought about if it cannot be represented by a multimodal Gaussian, if it is a completely different kind, like exponential or something else. But actually, fortunately, it was not. It was still kind of Gaussian, but then it was slightly different. Than,
so if you have a multimodal Gaussian, are you capturing the mean and standard deviation of each of the modes then, or are you just capturing a mean and standard deviation of the overall distribution?
The overall distribution.
I see.
Yeah.
So how does that work? Because if you have a multimodal Gaussian, the mean and standard deviation are relatively meaningless. They don't give you enough. They don't give you much information about the distribution.
Okay. You mean to say that if you take the mean and the standard deviation of the entire distribution, then it doesn't make sense?
Well, it gives you some information, but not very much, because if you imagine like 3 peaks, let's say if it's 3 modes, you have three peaks somewhere, and the standard deviation doesn't tell you very much, and the mean tells you a little bit. It tells you where most of the data is concentrated, but with those 2 numbers, you couldn't possibly reconstruct the distribution.
Yeah, exactly. It's not actually 2 numbers. Like you said, if it has 3 peaks, then we'll have 3 different means.
Oh, okay. That's what I was asking. If you got the mean and standard deviation for each of the modes.
Yeah, each of them. Actually, I didn't hear you.
Okay, that makes more sense. Yeah.
That's why it's much better than the KL divergence, because like you said, the KL divergence will look for only one, and only one of the standard deviation. So it makes much better sense than this. So effectively, we reduced the reconstruction error, and it worked out pretty well. And so now my supervisors, they are looking at using kernel density estimation to actually find out what the distribution actually looks like. For these kind of things, the more physicist domain knowledge is required. So I'm not actively involved in this particular part of the research, but I'm kind of involved in this one to see how it deviates from normal behavior. So yeah, that pretty much concludes it. And if you have any other questions.
Yeah, so could you, I must have missed it when you talked about what an L1 trigger is. What is the L1 trigger?
Okay, let's go back here. Okay, so L1 triggers are like a very, so you see this in the CMS detector, it detects a lot of things. It can detect, I'm not exactly an expert, but I'll just share what I understood from my talks with the physicists. So they told me that in the detector, they have lots of detectors from muons and different kinds of particles, because you can actually see the decay of the energy, and then using the path, you can say, okay, a muon was detected, or a proton was detected, or some kind of particle was detected. So what this L1 does is very basic. It just detects a very basic thing. For example, it just detects if there was a muon or not, or if there was a proton and how long did it last, or something very simple. And then in the high level trigger one, they have very sophisticated, like they try to find out, okay, if there was a proton and there was a muon, then it might be not so interesting. But if there was two muons and one proton, then it might be interesting, or some kind of very deep kind of sophisticated stuff. So that's what L1 triggers actually detect.
So your experiment detects the L1.
No, it tries to map a correlation between L1 and the HLTs, how they are correlated, like how one impacts the other. Basically, they are seeded. That's the whole design. So if you have, like, I can show you here. So basically, you can see one name of this L1 algorithm. I don't fully understand it, but as you can see, there is muon here, and there is this tau something, and then you see this give rise to these four different. These are related, correlated to these four. Is isomuon, then medium charged iso, and something cross LN and something. And so these are like how it's related. So you have lots of these, not just one, and there are lots of these, and they are correlated in multiple different ways. And each time you do not throw in all of these, you throw in one which might be correlated to these five. This is just for an example, but it could be many, this could be many. And then you just try to find out if you can learn the prior, which gives rise to this. This, like you can also imagine, it will actually do better than if you just throw in an HLT and then try to predict the HLT back here. Because this L1 actually, in a semantic sense, gives rise to these HLTs.
So Aman, thanks. I
Yeah.
think that was really very cool. I have a further question, or I want to recapitulate what I understood. Sort of the problem is sort of like you essentially did data engineering because of these massive amounts that are gathered at CERN, and basically you need an automatic sort of pre-filter what data gets through.
Yes.
And what the part that I didn't understand, and how do you collaborate then with the physicists? I understood also that some physicists are involved and they need to say what kind of data gets through. So how does the collaboration between the algorithm and the physicists then work?
Okay. Yeah, that's a very interesting question. What happens is when CERN was built, there were only physicists working at all of these systems. So they were the ones who actually implemented the L1s. These are actually done in the FPGAs and the ASICs, basically in hardware. And this one is the software part, the HLTs. And this one was done in collaboration with software engineers. Basically, they told the software engineers that, okay, this is how it should look like. And together they built up the code. And the physicists have the very dark knowledge, the deep knowledge. Only they know how this and this is related, and not the software engineers at all. So that's why they have command centers that run for like 3 or 4 months, that runs 24 hours, and you have one field expert always sitting there, and they have shifts. So every 6 hours, people change spots, and those are the physicists that actually look at these how it's behaving, and which ones are firing and which ones are not, and only they understand, okay, this should not happen and this should happen. So that's what is being currently done at the command center.
Cool. Okay. And did they tell you what do they want to detect there? You mentioned protons and muons, and what type of particles? Maybe Joseph can chip in as a physicist. What type of particles they wanted to detect in there?
Actually, from what I understood, they didn't basically tell me, but from what I understood, that there are lots of research groups within CMS experiments, and each of these groups are trying to look for certain kind of patterns or some kind of particles specifically, and they also collaborate across each other. There is also this, like I showed you in the video, there are 4 different major experiments. So each one of them looks at the data independently and captures the data independently, and the collisions and everything. And in the end, when they find out something, they are not specifically looking for some specific kind of particle. They are maybe looking for some kind of pattern. Last time I heard, they were looking for SUSY, supersymmetry, and I don't understand what that is, but that's what I saw in the posters, and they were talking to each other about it. And in the end, they just they match up their findings across the experiments like Atlas and CNS and see if it matches what they're expecting from the theory and how it looks like in the experiments. And if it doesn't match, then that's a breakthrough. And if it matches, then what they said me was that's like normal, nothing interesting there.
Okay.
They are basically looking for deviations from their theory, so that they can find out.
Would it in principle then be possible with the, you know, when you apply these data engineering algorithms and pre-processing algorithms, that in theory something could be missed then, and maybe something important could be missed?
Yeah, exactly. That's the difficult part of it. Something definitely can be missed. And that's why they have a field expert always sitting there monitoring this system so that they don't go haywire. Because if something goes haywire, then basically the 3 months data is just wasted, and it takes huge amount of energy to run these experiments inside. So yeah, that's a concern. That's why they are trying to improve and add more filters and add more engineering on top of it. Okay, are there any more questions? Do you want to look?
Thanks, Aman. That was really interesting.
Yeah, thank you.
Yeah, and thanks, Aman. And there is nothing on a chat window, so I think it's off.
Okay. Yeah. Okay, I'll stop sharing and someone can take over from you. Okay. Thank you, everyone.
Yeah, thanks again.
Aman, yeah.
So, go on. So, who is Michael? Do you have an idea who is presenting today's the lecture?
Actually, I was supposed to present that, and
Okay.
I discussed with on the host group. Actually, I didn't finish much later than a significant part of it. So
Oh, that's no problem. I think it's with probably most of us.
yeah,
You have to go through like 2-3 times. That's
Yeah.
fine.
Shall we go with what we have anyway? Just to start, and then we can.
Yeah,
finish it.
some of us must have taken notes. That maybe we can just talk a little bit about the notes that we took. So the first thing that he presented.
Okay, so yeah, well, like I have just 4 or 5 lines. One thing which he started with was the mix-up.
Yeah, it was mix-up. There was the label smoothing thing. There was the ResNet thing, and then the NLP kind of block.
Yeah.
So some interesting topics, I have to say.
One of the question, yeah, with the mix-up, I think he explained very well. But one of the questions somebody asked during the mix-up was, how does it help? How does the mix-up actually help in normalizing? He tried to explain it, but I didn't get the answer. Anybody has an idea? In general, let's say if we say 70% of 70% of, I think he has a 1 and 30% of the other picture. If you mix it up, it's normalized better. It helps. How? Anybody got the intuition for it?
Yeah, I think so.
The idea is that the mix-up it's like data augmentation. So you get all you can have an infinite number. You can draw an infinite number of new samples based on the samples that you already have. That are, and the new samples are basically linear combinations of the old samples. Well, they're called affine combinations of the old samples, where the affine combination is, say if you have 2 samples, the mix-up is a probability, you draw some probability, and it's kind of a combination of the 2 states. So if you draw the probability 0.7, then your mix-up is 0.7 of state 1 and 0.3 of state 2, and you add these together to make a new state, and that's basically generating a new sample for your data. And so the mix-up is allowing you to expand your data set, like data augmentation.
Can we mix up more than 2 images?
The mix-up is just 2. So every mix-up sample is just
In theory, I don't see a reason why you couldn't mix up more, but I think the paper is looking at just did too. But he did talk a bit about some.
I mean, that's right. That's right. In principle, you could mix it more than two, but they've got an elegant way to combine two samples by using a beta distribution. You draw the probability from the beta distribution, which is specially peaked. It's peaked at 0. And, well, it's peaked. It's bimodal, and it tends to go high at 0, and it tends to go high at 1. So you're getting you're not getting sort of murky samples that are drawn from half of one sample and half of the other. They're more like just a little bit of they're mostly sample 1 and a little bit of sample 2 thrown in.
What were your guys' thoughts on? I thought one of the really interesting things he talked about was using it in NLP on like a let's say a matrix embedding of a sentence or something like that, and then kind of mixing up the input. So let's say you have like, you're predicting if the email is spam or not, and you take each word, you do like something like word to vec, or you embed it, and then you have a matrix for each email. And so I think my intuition was that you then, similarly kind of combine those matrices in some way so that it's, let's say 70%, a normal email and 30% a spam email. And I thought that was really interesting because like text data, I feel like is one of the hardest to augment successfully, but it seemed a little different than images too. So I was curious your guys' thoughts.
I just thought that the using an embedding vector it seems more straightforward for me to understand what it's doing than if you're using an image. Like, so what does it mean if you combine 2/3 of a dog image plus 1/3 of a cat image? That's kind of weird, but it works. But to me, it's more intuitive to think of you can combine linear combinations of these embedding vectors to get a new embedding vector, and that to me makes more sense, that you're really doing some augmentation of your data. And the exciting thing is you can augment it to your heart's content. You can generate as many samples as you want to extend your data set.
Yeah, I definitely like to try to play around with a little bit, see if I have anything to report back.
Okay, and
did anybody pick up on what that is? I kind of missed what that is when we talked about label smoothing. Because he has to handle, like, you mix up the training samples, but then you have to mix up their labels too. And did anybody get how you do that? How the mix-up works on the labels?
I think I made some notes on label smoothing. You mean with label smoothing with respect to images, right? Because I'm still on the image part of the
lesson. Yes.
Yeah, so my notes I think read was softmax isn't going to be very good at identifying targets with mix-up. So to really use the mix-up well, anytime the labels are not 100% correct, so we don't do a one-hot encoding of the labels, but say 1 minus epsilon, or where epsilon is like the noise amount which we are subtracting for the correct class, and so the correct image would be 1 minus epsilon, and epsilon would be for the other image, which is like, if it's like a 70% dog and 30% cat, then it would be 1 minus 0.3 for dog and 0.3 for cat. That would be the label. And then you'd probably have the label smoothing cross entropy function designed accordingly for that.
Okay. So you're basically mixing up the labels. That part I understand. 0.7 of dog and 0.3 of cat. So instead of each image having a single label, now it has a combination of 2 labels. But then what do you do? I mean, how does the
so the label smoothing is like useful, particularly with mix-up, but it's something kind of separate, and you could use it if you're just doing one class. Basically, like, think about it this way. Do you remember that picture was going around the internet of like the blue dress, and it was like half people were like it's blue, half with gold stripes, half people said it's something else. So the idea is, like, let's say there's something where for whatever reason it's not a definite yes, it's this category, and maybe you're 90% sure that it's this category, The idea is instead of your target being a vector of all zeros and then a 1, it might be like all zeros and 0.9 for the target. So you're like reducing the confidence you have of what the actual target is. And that acts as like a regularizer.
Okay, okay. Okay, that makes sense.
Yeah, that was a really good explanation.
Yeah, I didn't know if the blue dress thing was going to work out there. I was hoping somebody else had wasted time looking at it.
So then they talked a little bit about mixed precision training. Jeremy said that in mixed precision, and you can't always do mixed precision training unless you have the right kind of GPU. I think the NVIDIA RTX GPUs can do mixed precision training, but the GPXs can't. Sorry, the GTXs can't do mixed precision. But Jeremy said that when you do mixed precision training, you have to do you do the forward and the backward pass in FP16. That means with a half precision. But you do the rest in FP32 to avoid round-off errors and runaway errors. So I did, yeah. So that's just sort of a heuristic that Jeremy told us, but I don't really have an intuition for why it's got to be done that way. But I did remember that he said that. And then he said that NVIDIA has this Apex library for mixed precision. So I made a note to look that up. I haven't looked it up yet. I'm just going through my notes. He says that you can get, and I know that Sonia knows a lot about this because he's done some systematic experiments with mixed precision training. So, but he's not on right now. So, but Jeremy said you can get 2 to 3 times speed up for vision, for imaging, for processing images and so on.
What I also found with the FP16 with the mixed precision is that you sometimes you can get better results, which is kind of counterintuitive with the FP16 instead of the half precision numbers instead of the FP32, and this is kind of not well understood, but kind of it can work like regularization in some way for a neural network.
Yes, that makes sense. That it can work like regularization.
Yeah.
Because basically, you're just putting a constraint on how accurate the number is. You're forcing it to be less accurate than you've calculated it to be, and yeah, I can see how that could act as regularization.
I thought that's kind of like a side effect, kind of helps you.
Yeah. Then he talked about dynamic loss scaling. I don't understand what that is. I have to look that up. Does anybody know what that means?
Not so sure.
Okay. I have that idea. He went into a lot of details of the res block architecture. He talked about convolution layers and pooling and no-ops and strides. All of this is from the Bag of Tricks paper, so that's definitely something that you have to read to understand what he's doing here. So Jeremy said to read that paper and understand all the tweaks, and he said, think through the architecture design so that you understand what the architectures are doing. This is all stuff that is on my list of things to do, but I haven't done yet. And he ended up refactoring the hell out of it so that at the end he got this thing called an X-ResNet that fits on a screen. So it's very compact. Jeremy's all big on refactoring and compact coding, which is good, I guess. But when you look at a piece of refactored code that's been done so that Jeremy has put so much work into, it's really hard to understand what it's doing. And I think that's the big challenge. If we could understand what he's doing with that refactoring, that's probably the goal of this class, is to understand the software engineering that goes into that refactoring. Anyway.
Yes,
So
I
he
think
then, Sorry.
the ResNet. So the ResNet, so he pointed out that in original ResNet, the first convolution was the 7x7 kernel, which everyone used for like years. And now seems to be that's not the right way to do it, as it kind of like a waste of resources, compute resources. I have something like that, I think. That's what he said. So now what the paper suggested that the first kernel should be 3x3. And that gives you a lot less numbers to crunch, right? That's my understanding.
Yeah.
And also the stride thing, kind of like the initially, yeah. So once you have 3x3 kernel, because the 7x7 had stride 2, but if you apply stride 2, because I think they also shifted the conv1, the 1x1 kernel to the first as the first kernel. So then the stride 2, which was in the first place, wasn't making any sense. So they kind of like tweaked some bits and pieces here and there, and they've managed to get some nice results. So that's really interesting to me. Like there is like the standard to do for like years, and then all of a sudden there's this, no, that's not actually the right way. Let's do it differently. I find it amazing. It actually that it develops in such a ways. But how to be on top of all of that, it's kind of such challenging.
Yeah, but I think that the key thing for this lecture is to go through that bag of tricks paper and understand it, and then go back and understand the code that Jeremy and Sylvain have written. I think if we could do that, that would crack the nut of this whole lesson, I think. So that's the next thing to do.
I agree.
I had a few doubts on some terminologies related to CNNs. One was, what exactly is a receptive field? Like if we talked about the receptive field of a kernel, like what would that be?
Yeah, I remember it saying that.
Okay, that's interesting. Let's
And one more thing actually I wanted to ask is, like you have the ResNet 18, ResNet 34. So the 18 and the 34, what do they stand for exactly?
I think the 18 and the 34 stand for the number of layers, the number of ResNet blocks that are in there.
Okay.
So the bigger the number, the more blocks, the more ResNet blocks are in that network.
Okay, because when
also the longer it takes to train, I think.
Okay. Because when you was making the XResNet blocks, the XResNet 18, I was counting I think the number of filters or layers. I think it was exactly half of the number he was specifying over there. So I think if you see the notebook for the training.
Yeah, I remember Jeremy saying on Twitter that there is still kind of lack of general agreement between the deep learning community and like the number of layers. They still don't really agree between themselves what is the layer in the network. Is it only the ResNet block, the like the convolution? Is it the activate? Is it the ReLU like function? So I think this is still kind of like open for proper definition. What's actually a layer in a network? So I think your point is really valid, like how to count the layers.
Yeah, because I pasted in the chat one of his, like he was creating the XResNet 18, the XResNet.create. I'm counting 9 and there's 18, so I was a little confused.
I had one question. Did anyone? I know the original ResNet when it first came out in 2015. It had 152 layers, right? So it started with 152, and then there was ResNet 101, ResNet 50. Does anyone know the difference between XResNet and the ResNet? what maybe there is, maybe that might help this, figure out this discrepancy between 18 and half the yeah, what's the difference between X ResNet and the original ResNet?
I thought he basically said X ResNet was like a ResNet with all the tricks from the bag of tricks paper put into
I
place,
see.
something like that. But I could be wrong on that.
No, no,
Well,
that
I have that in my
is
notes
correct.
too. Yeah.
That is correct, because I think he showed it in the one of the pictures, the figures that was there in the paper. Instead of I think the ResNet equation is you add the con players plus the input after every 2 or 3 con players. And I think in the bag of tricks, instead of just adding the input, they were passing it with a max pool and then another con player. So that was the X part of the X ResNet, I guess.
See. Thanks.
Yeah, the advantage of it is that you can train it with high learning rate, so that it trains faster.
Thank you.
Yeah, I just went through the some of Leslie Smith's papers this week about like super convergence, and I feel like I'm about 2 years behind at this point. But it kind of blew my mind how fast some of this stuff can learn well.
One doubt I had was he'd asked I think in one of the X ResNet blocks there was putting a batch norm of 0 at the end, a batch norm layer which was initialized with all zeros. I think it was when he was making the conf layer, when you were initializing the batch norm weights, it was 0 if 0 underscore bn, this line. I'm just pasting the function in the chat window. So I think there's this line over here. Initializing the batch norm weights to 0. He said that really helps when you have really deep networks. But I was actually confused because for me it was everything would then become 0. So basically the entire layer, I'm not sure what's the point of having that con there. We're just passing the input as it is. Because if the batch norm weight is 0, then the entire multiplication becomes 0, right? Or am I missing something?
Yeah, but it looks like he's not initializing everything to 0. He says that if something, then 0, but but otherwise initialize it to 1. So right. 0 if 0 bn else 1. There's that line. So I'm not quite sure I understand what that line does. Oh, but then 0 bn is false. Sorry.
I was just saying, I guess I don't really get it either, because like if it's 0, doesn't that mean it's almost impossible or impossible for it to turn into something?
Right, exactly.
I think I remember actually. Isn't it because there's like a residual connection that the idea is that sometimes you would want it to be 0, because if it's 0, then you're putting what was a couple layers back through without changing it or something like that. I was kind of falling asleep towards that part of the lecture, so
Yeah.
I might be remembering that wrong.
Yeah, that part. Yeah, that could be true. Because he was going on that maybe that helps in really deep networks, So I think if the
I think I remembered that part where it said that if you zero them out, what it basically does, it reduces the depth of the network. And like this, it's the theme of the entire class that in the beginning of the training, you want it to be really good, as good as possible. So in the beginning, if you have lots of zeros, you zero out lots of layers, then technically it's kind of shallow, and then it helps the training in the beginning. That might be why.
So is it like stochastic or kind of random that some are going to have 1, some are going to have 0?
I
That's
think
what
it's
I think, but I don't see how it happens because he set 0bn to false. 0_bn is set to false, and I don't see anywhere else where 0bn can be anything else but false. And then if 0bn is false, then the weight gets initialized to 0 every time. So I don't quite understand how this works, but it's got to be something like you said, something stochastic where some of the weights are 0 and others are 1. I just don't see how it happens.
I think I found something. If you look at the rest block class code, when he's initializing the layer, the first layer he's put the 0bn to true. Wait, let me look at the equation again. Yeah, so let me just paste this code snippet over here on the chat window.
Okay.
So I think it goes something like this. If expansion equals to 1, else if you see one layer has no 0bn mentioned, so I guess we assume that 0bn is false, and in the other one 0bn is true. So I think he's decided that the initial layers he's put the 0bn, or if you look at the code where 0bn is true, he's explicitly mentioned it. So maybe it's not stochastic, but he's done it in a, let's say, in a fixed way. Like there's no pattern as such. Like if he's initializing 3 layers, he's writing each of the 3 layers in the class. Like there's no loop.
What's ACT? ACT.
Act would be activation for the ReLU.
Okay.
Oh, I looked. It's just a ReLU function. Like it's just kind of hidden in the code a little bit. It's just nn.relu. So what's weird is I don't see anywhere in his ResNet where 0 batch norm is not equal to true.
But in the line above, in the line that Abhinav pasted above, there was it was explicitly set to false.
Oh, I get it. I get it. So like if you do, when you call the conv layer function, if you're not explicitly saying 0 batch norm is true, then it's, you know, by default it's false. That makes sense.
Yeah, I think so. Yeah.
Yeah. So I guess the takeaway is that it's the weights are not always set to 0. So that confusion is resolved. Although I still don't understand the fine level details. So he talks about this thing called discriminative learning rate. And he's talked about this before in course 1, where he splits the parameters into 2 groups. One of them is the deep layers of the network, and the other layer is just maybe the last couple of layers. And I'm just reading from my notes. I don't really understand this, but the first group, you don't use batch norm, and the second group, you do use batch norm. So he implemented something like that. And then he tested it and made sure that it worked, and that's all I got on that. Then he says that Jeremy says that cross-validation is pointless in deep learning. And I think the reason he gave is because the validation set will always have a huge number of examples in it. And so you don't really need to do cross-validation, because the only reason why the reason why cross-validation is used is because often you have small validation sets. This takes advantage of, say if you have 100 examples in your data, and you're doing 5-fold cross-validation, then each data set has only 20 examples in it. And so you have to average them together to get back your 20 examples. But with 1,000 examples already, even if you take, 1/5 of them, you already have a large number of examples to work with. So he says you just don't need cross-validation. It's just, cross-validation is really time consuming too. So that's a good thing if you don't need it.
Yeah, I think he was also talking about cross-validation in his machine learning course, even more when we're talking random forest and stuff. So
yeah,
if you choose your validation set carefully, you kind of choose whatever should work best for your model. Whereas with the cross-validation, you kind of get like the whole, or even randomly, you choose randomly some data points from your data set. And that's not necessarily the best choice of your validation set, especially, for example, if you have the time factor in your set. So then you want to choose the time range that interests you, like most likely the last kind of couple of weeks or months. If you want to predict the future, you want to kind of base it off the last available data you have. But how that relates to like the image data or other, I'm not so sure. Whether that relates at all to cross-validation to image, I'm not sure.
Yeah, another point about that is that when you're using random forest or any other tree-based methods, you don't need you don't need cross-validation, because random forest gives you sort of a built-in cross-validation. You can use the out-of-bag samples to predict your generalization error. So you don't really need cross-validation.
Yeah, although when you look at Kaggle and kind of top scoring kernels, almost all of them use the cross-validation with the XGBoost. So I'm
really
that,
okay.
like,
I didn't realize. I haven't ever looked at any of those, but that's kind of surprising.
Maybe
Because
it works different. Maybe the
SGB
XGBoost works different. I'm not so sure. Maybe the XGBoost works differently. Yeah.
I just know the point I made is true for random forest, and I assume that all the tree-based methods are similar, but maybe I'm wrong.
Yeah, one of the Kaggle grandmasters gave a presentation on like k-fold cross-validation, and I was really shocked. Like, why is he talking about k-fold cross-validation during like for 40 minutes?
Yeah.
And I was like, what's there to talk about this for such a long time? Especially we have such big data sets, and they haven't shared the slides, but if I in a few weeks they will share the video, and I will share it with the team. He was making there's a thesis from like the late 90s, and he was showing about he was making a big deal about choosing 5-fold and 3-fold cross validation. And even 5-fold, 10-fold, 3-fold, and when when to use in what scenarios. And there was if I find the video, I'll definitely share it on the chat.
Oh, that'd be great. I guess that you know, between threefold, fivefold, and tenfold, the difference among them is that you sacrifice precision for speed. Like threefold, you can do it faster, but you get less benefit out of it. Whereas
Right.
tenfold gives you the most benefit, but it takes the longest. And then of course and that takes the longest because you have to run the model once for every group. You have to run the model essentially once for every example, but that gives you the most precision. Yeah, so I think the trade-offs is all about speed and precision in that. Then in my notes, I have the next thing he did was he talked about debugging tips. And somebody asked him about the best debugging tips, and his first answer was don't make mistakes. But he went on to say, try to simplify your code as much as possible as you're writing it so that you can clearly see what you're doing, and check every intermediate result, and keep track of all of your code changes in some kind of a journal. You know, so whether you do it as in GitHub or you have your own method of keeping track of your code changes, that's a key thing. And you know, in my own personal work, I just try to document. You know, I spend more time to write code than most people because I spend a lot of time writing comments, so that when I come back to the code, I'll understand what I did. I mean, some people have a wonderful memory and they can look at their code and then 3 weeks later they can come back and say, yeah, I know exactly what I'm doing. But for me, when I come back to code that I've written 3 weeks ago, if I don't document it, I have no idea what I'm doing. And so I force myself to write down exactly what I'm doing. And then later on, when I go through it, I can look at those comments and say, oh, you know, you screwed up there because that's not what you're supposed to be doing. You know, in other words, I wrote down clearly what I did. And then when I come back and look at it, I can see that it was the wrong thing to do. And the only reason I can see that it was the wrong thing to do is because I wrote down exactly what I did in the comments. So that helps me.
It's maybe a good option to make a lot of assertion, yeah, or maybe a lot of tests to do, because this is that when you give this two values and this will give you this output, so you now what is correct answer and how it's work.
Yes, that's a great point. He did make they call that test-driven development, and he made a big deal about that. That exactly what you're saying. You write unit tests, little unit tests at every phase of the code, and you don't let yourself get ahead of the game. You just keep it, and then move to the next block of code, and you write more code, and then you write another test. You don't write a huge block of code without running tests all along the way. I guess that's what they call test-driven development.
Joseph, if I can chip in here real quick, I think not making mistakes is not realistic, because after all, we are all humans. And so I would agree with that. I mean, the best thing is also the test-driven development is a good idea, and also formal version control via GitHub is the way to go here, I think.
Oh yeah, absolutely. I mean, the not make mistakes is just a joke, really, I think.
Okay.
I like even Jeremy, when he was giving like examples of the mistake they did with like one of the PRs in the library, and they didn't notice for like weeks or months, he said, because even the guys like them, it's so tough, especially like when Chris Latner, where he's like software engineering oriented guy, when he asked Jeremy, how do you data scientists, how do you debug your code? And he was like, yeah, most cases they don't, mostly. So that's the kind of interesting observation, I thought.
But also interesting is that in most softwares, for bugs are, for example, for 10 years, and nobody find them for about 10, maybe 15 years even. we can still find some new bugs.
Yeah, I think
this is natural.
The way to get around that is to have code reviews where people look at your code, like have a lot of eyes on your code. So you know, every week you present your code to the group and have them, you actually put it up on the screen and have them look at it, and you know, you explain to them, and then many eyes looking on the code, there's a good chance they could find the bugs that are there. I think. Okay, after debugging, he talked about ULMFit, that's where they developed transfer learning from a giant dictionary taken from Wikipedia, and they built a language model on that, and were able to use translate. I guess in 2018, maybe roughly a year ago. But then that ULMFit, that meta transfer learning, can be applied to any kind of sequence analysis, not just language modeling. And he talked about some examples. He was talking fast, and I wrote down one or two. He talked about chemical bonding, and he talked about genomics. Chemical bonding, I didn't quite understand the connection there, but genomics you can easily understand, because genomics is basically looking at sequences of DNA. And so, you know, you could see how, you know, language modeling could be applied, or language modeling type techniques could be applied to genomics. Okay, so this is like an hour through the lecture, and so I guess, as I said before, for the first hour, the thing to do is to read that that CNN Bag of Tricks paper. That's mainly the core of that hour. If we do that, we'll understand most of what he did in the first hour. But then in the second hour, he just goes nuts, and he says, "I'm going to recreate the you know, the process of applying ULMFit to the AWD LSTM." I think he talks about this. He talks about this. He says ULMFit is transfer learning applied to he talks about LSVMs, but in the next few lectures, but in the next few notebooks, but he says that he recreates this process from scratch in the next 4 notebooks, and then the fireworks start to happen. So he just does all this stuff really, really quickly. And I'm just going to page through. He gives a really nice diagram of an LSTM cell, and so you get some intuition about what it's doing. So, you know, it's I reproduced it in my handwriting. I can't really show it here, but it's worth. Short-term time correlations in data. So like if somebody's speaking and they're talking, then, you know, from a few sentences, you can predict what they're going to say next. That's what a language model tries to do. So you can imagine that you're looking at, you know, maybe, you know, 50 words or something like that. And then, so you're looking at the time structure of 50 words and then trying to predict what happens next. But I think people have been successful in going way beyond 50 things. I'm getting ahead of myself, but somewhere in here they talk about looking at 1,000 sequences of 1,000 words and having models that can successfully learn the time structure in 1,000 in a time series of length 1,000, which is, so things are getting a lot better in that respect, is being able to go to longer and longer term sequences. I'm afraid that my notes are really sketchy here. He talks about dropout and variational dropout. I don't know what that means. Oh, and this is dropout being applied to language modeling. So I'm not quite sure how in practice it works. The concept of dropout, I understand. In networks, you're dropping the nodes, but I'm not sure what dropout means in the context of language modeling. And he refers to Stephen Merity. I think there's a paper that Stephen Merity wrote on this ULM fit, and I think Jeremy was one of the co-authors. Maybe he refers to that paper somewhere. He talks about another kind of dropout. Okay, Stephen Merity introduced these new kinds of dropouts for language modeling. The first one was just basic dropout, and Jeremy implements it in a class called RNN dropout. And the second kind is called weight drop, where you drop, and it's called also called drop connect. And it applies dropout, the concept dropout on weight. So it basically selects some weights and zeroes them out. That's what that is. And apparently that helps. And then he talked about the third one was embedding dropout, where you drop out an entire row in, I'm not quite sure what he means by an entire row. So sorry about that. Then he shows all this code. He's implementing all this code as he goes along, and he talks about gradient clipping. And I think we understand what that means. Gradient clipping will limit the value of the gradient to make sure that it doesn't get very, very large. And so that takes care of that sort of by hand takes care of the runaway gradient problem, the exploding gradient problem. And he says again that gradient clipping allows higher learning rates. That's the key to a lot of these modifications, is you want to be able to train your models faster, so being able to train your models successfully with higher and higher learning rates is basically the name of the game. And I think that's what Daniel, you were saying about Leslie Smith's papers. That's one of the things that he was trying to do so successfully is finding ways to train with a higher learning rate. Let's see. He talks about a whole bunch of concepts, new concepts, activation regularization called AR. He puts an L2 penalty on activations. I understand the words, but I don't understand exactly what it's doing or why it's good. He talks about temporal activation regularization, TAR. I don't know what that is. I'm just going through my notes. I was writing as fast as I could while I was listening to it. Let's see. He says that training Wikitext 103 takes 5 hours, but and that's on his machine. He's got a pretty good machine. But he said they've done it for you so you can download the entire pre-trained model so that you don't have to do that training, when you're running these notebooks. You don't have to train it for 5 hours. Or more likely more than 5 hours, because you probably don't have as good a machine as he has. Let's see. Okay, and that was basically it. That's 1 hour of going through module after module, class after class of code. So that's going to require a lot of study to understand that. And there's 4 notebooks in the last hour. That's the last, actually, that's probably the last, yeah. And then the last half hour, so it was a 2.5 hour class. The last half hour, he talked about Swift. He and he actually had Chris Latner on there for a little while talking about Swift. And
he talked also about JIT compiler.
Oh yes, he mentioned something about that. They're trying to implement that, and they're having a lot of trouble. I think it's not quite ready for prime time yet. So I don't understand what that is. Can you explain more about that? The JIT compiler.
I only know from what Jeremy said is about that this compiles the Python code into C++ code, so it runs faster, really much faster, and compiles so it really much faster than when you write in the Python code.
So you can take any Python code and run it through this JIT compiler, and then once you have the compiled module, you can run it very, very quickly compared
Yes,
to...
yes, because in C++ you usually don't have some garbage collector, you don't have some memory management, and so this is made in C++, I think. So in Python this takes a lot of time. This building functions. So this was I understand by this JIT compiler.
Okay, so it looks like Swift is by its nature intended to overcome that problem, because it is a compiled language and makes everything and it's sort of it runs everything as fast as possible, I think. In other words, when you get things working in Swift, that's almost as fast as it can be. So he's giving many reasons why he thinks it's useful to look at Swift. And he says, I'm just going to read some of these because I copied them down. He says, deep learning libraries change. He says, Python's days are numbered, and you're going to need to learn something new in the future. Python's days are numbered, I guess, just for that reason, because it's relatively slow compared to C++. He says that the next new thing is going to probably be either Swift or Julia. And he says, learning new languages makes you a better developer. So that's a good point. And he said TensorFlow is being overhauled from its foundations. And right now, TensorFlow is probably the it is hands down the most popular deep learning library. So if TensorFlow is being overhauled, then and to work with Swift, then there's probably a good reason to learn Swift. The other thing that makes Swift exciting for him is that the landscape is open for your contribution. You know, it's wide open. They need people to write new code for the you know. So that's probably one of the reasons why Chris is talking in the last couple of lectures, because he wants to recruit a bunch of us to help him. So he says you don't need to already know Swift. You can just jump in. He says aligning yourself with successful people is good, and that's an obvious truth. And here we have two successful people that we're aligning ourselves with. One is Jeremy, whom we've already aligned ourselves with, and then Chris Latner, who's been a very successful person in his own right. The Swift community needs our skills, and Swift lets us explore little touched areas. I copied that down word for word. I don't know what he means by that, but I'm interested to find out. So this was all Jeremy introducing things. Then let's see. He talked about learning. He said, "Do you really need to understand C++?" I think this is okay. They next open it to some questions for Chris, and Chris recommended the first place to go when you're starting to learn Swift is at swift.org, and they have documentation there, and it's called a Swift tour. That's the place to start. Then they asked him, what are the goals of the Swift projects? And he said, we're going to be very subtractive of complexity. I guess he's trying, that means simplify things as much as possible. He wants to integrate deep learning into the applications. So right now you build your model, and then you build your model in TensorFlow or PyTorch or whatever, and then that stands alone, and then it has to be integrated into other code. For example, in order to serve that model online or to deploy it, so that users can get at it. But I think that the point of Swift is he says, to remove the barrier between the machine learning piece and the application piece. So presumably you'll have seamless, you'll write your modules and its deployment seamlessly in one module, in one piece. And then he said, somebody asked, do we need to understand C++? And he said, learning C++ is good, but using C++ is not a great experience. And that was particularly interesting because Chris Latner is one of the people who wrote, or he has written C++ compilers. So when he says using C++ is not a great experience, it means something. I don't know about, I'm sure most of you out there, many of you out there have C++ experience. I've learned it, but I've never really used it. So I understand something.
Yeah, it wasn't the easiest experience. It wasn't the best. Like, it wasn't easy writing C++ code. Like there's a lot.
Yeah.
I think with Swift, I have like some experience of Swift when I was like trying to learn iOS development. And I think one thing with Swift would be that the callbacks would be much more clearer with Swift, because since it's a static language, the way the types are defined, callbacks would be a lot clearer and easier to read and understand in Swift than it is in Python. I think in Python, with a lot of the done magic methods like getAttra and setAttra that he was using, it was a little confusing to understand. I think that part would be easier to understand in Swift. I'm really interested in how the data loading part and everything goes on, because Python has a lot of helper libraries like Pillow and Pandas, and how Swift manages for that.
Yeah, and that's the one thing I remember from C++ is that it's a pain in the neck because you have to define every variable and give its class and so on. But so that's a pain in the neck, but it's a double-edged sword. It helps too because every variable is clearly defined, whereas in Python things can get confused. Anyway, that's the end of my notes. That was the end of it. So there's a lot in there. There's a lot in there, but the main thing I would think is the Sin and Bag of Tricks paper, to read that and really understand it and go through some of the notebooks that Jeremy's done with that. And then the second part is understanding these last 4 notebooks where he goes through and does basically does ULM fit from scratch. Again, those are a bunch of notebooks, a series of 4 notebooks, and we studied them closely and tried to understand them. I think we'll get the gist of the second hour. And then the Swift introduction is a good preparation for the next lecture because it's going to be Chris Latner talking about Swift. Is it going to be Tuesday or Wednesday? I forgot. Is it Tuesday? This week?
Tuesday, I think.
Tuesday,
I think
yeah.
it's Tuesday.
Yeah. Okay. So.
And then we're supposed to have some extra lessons as well about the stuff that didn't fit.
Yeah,
in the,
yeah, and I'm particularly interested because he wants to talk about audio processing, and that's really interesting. And they're building an audio component for the Fast.ai library apparently, and this is going to be the first he's going to give us an introduction to that, I guess, and then eventually we'll see it. They'll finish that library and it'll be available to everybody. Anyway, so that's it.
I guess a lot of homework for this week.
Yeah.
Yeah, I feel like there's a month worth of stuff in one lesson.
Yeah. So the way I look at this is it's going to give us, it's just like he said at the outset of the course, he's going to give us a lot of work to do between now and June. And I think it's going to really take that long to go through all these lectures. And I think that's what we can occupy ourselves with after this course is done, is just going back over all this material and really understanding it. I think that would be a really worthwhile use of our time between now and June when the course is going to come out.
Yeah, I think that's the discussion we started in Slack about where you should put your time and energy with all this stuff happening about the Swift, Julia, the TensorFlow or PyTorch, Fast.ai. So many things happening. It's just crazy.
Yeah.
It's
I would vote for. I mean, I would vote for just when we finish the course, just go back to the beginning and go over it again, just for the next couple of months, and just review everything, because each one of these lectures is certainly more than a week's worth of work. To especially the poor guy who had to summarize it for today. I can understand why he had trouble. The lecture was Wednesday, and that gives him 2 days to prepare it. And this lecture takes, I think this lecture would take a couple of weeks to absorb.
Yeah.
So, yeah. Anyway, so I guess that's all I got. Anybody else have anything else they wanted to talk about?
I'm good.
All right. Well, see you guys all online on Tuesday.
All right. See you guys Tuesday. Have a good weekend. Happy
Yeah, have a
Easter.
good weekend, everybody.
See you guys Tuesday.
Happy Easter.
Thanks a lot.